Okay, we will get started. Hi, everybody. Happy Monday, and welcome back to the PCAST Talks. So before we get started, I wanted to give just a few brief updates on the project. Of course, we're all happy the government shutdown is over and everything is back to work. Even better than that, the PRIMA General Observer GeoBook Volume 2 has now been posted on the archive. So this is, again, really incredible work done by Ariel Moulet and others on the team to edit this with more than 120 submissions, and we're so grateful to everyone who helped participate and submitted a case, and we're excited for everyone to be able to take a look through that and see all the really exciting science that can be done. Of course, we will also be at the AAS in January. There will be a PRIMA special session. That's going to take place on Wednesday afternoon from 2 to 3:30, and there will be invited talks from a number of folks in the community, also focusing again on highlighting some of the really wonderful GeoBook cases that were submitted. And then finally, we're still collecting little bits of excitement just to help propel us all the way through to submission of the concept study report and the site visit that will be happening probably in late spring. So I'll post this in the chat, but there's a form where you can just go and tell us all of the really great things, like all of your great sound bites, right, that we can then share with the committee and share on social media. So we have a bunch of talks still upcoming all the way into the spring, actually. Sorry, and that last one is not November 17th, that's our February talk, but we have talks on PAHs from Grant Donnelly, disks from Meredith McGregor, and then on polarization from Susan Clark. But today, we're all here to hear Kasia talk about her work on astrochemistry. So please go ahead, Kasia, and thank you so much.
Yep, thank you. Let me just now share my screen. Hopefully, luckily, can you see
great. Thank you.
Yeah, perfect. So, good evening, good morning, depending on the time zone. I'm very thankful for the opportunity to give this PCAST talk. And it's going to be about astrochemistry, but more specifically about using astrochemical diagnostics of feedback and star formation between scales, because I do work a little bit on extragalactic astrochemistry side, not just galactic side. And so the plan for today's talk is, I believe, quite simple, though maybe the whole path we're going to take and the story I'm going to tell you is not going to be very straightforward. So we will start with talking about why the molecules are such a great lens on the ISM, how the emission that we observe differ between scales and regions, and whether we can scale that, and of course how a far infrared probe can come in and help our understanding, a little bit focusing more there on star formation side of things. Let me just change the slide. So when we look at molecular emission from galaxies, we are not just seeing pretty lines on the spectrum. We are seeing also the imprint of the physical state of the gas. So chemistry is very sensitive to density, temperature, ionization rate, shocks, radiation fields, the history of the gas and dust, and probably many things I just didn't mention here. But I think the bottom line is that molecules can act as diagnostic bridge between the underlying physics and what we actually observe as emission. And there is this logical link between chemistry being strictly related to the physical properties of a given medium, but then chemistry can also alter the physics, for example, via cooling, and then the emission is again related to the physics and chemistry both at the same time, and what we will observe will depend on the amount of gas and dust, but also how much abundant different species will be, and what is the reservoir of a given medium, and what chemistry is driven by the underlying processes. So in the ISM, chemistry is incredibly rich and spans many different phases of gas. We will see different molecules in diffuse gas, dense gas, PDRs, hot core, shock, starburst nuclei, AGN environments, and many more. And as of very recently, I've double-checked over the weekend, we've identified around 340 interstellar and circumstellar molecules and about 74 in external galaxies. So following Maguire's analysis, the majority of detected species is actually associated with star-forming environments. So in principle, we have a lot of diagnostics, chemical diagnostics to work with. But because molecules are so tightly intertwined with the environment, and the diagnostic meaning doesn't have to be very universal. So before going into details, I want to just give you some examples, because probably if your astrochemistry is not your main field and not on your mind every single day, I can imagine it can be tempting to think that we can figure out what each species traces in the Milky Way simply as that, and then apply that to everywhere, because, right, I mean, in principle, it should be very similar, but unfortunately, it's not that simple. So take water, right? It's one of the most ubiquitous molecules in the universe. And in the Milky Way, we've learned that many of the water lines, they are tracing collisionally excited and often dominated by warm, dense outflowing gas that is associated with protostellar activity. But for example, in external galaxies, the same water line can instead be dominated by far-infrared pumping. So when we have absorption of far-infrared photons, that leads to this excitation to upper levels, and then we have the cascade to the lines we're actually observing. But the point is, the bottom line is that far-infrared pumping and collisional excitation in outflows is obviously very different, and is tracing very much different processes here. So the interpretation may really depend on the physical context, and it doesn't have to be straightforward. And another example can be C2H. So, for example, in the Milky Way, we found that C2H can trace UV-irradiated gas, but in external galaxies, the interpretation can differ from galaxy to galaxy. So, for example, right here, we are looking at NGC 1068 and NGC 253. So, in NGC 1068, it was kind of more associated with the turbulent interference of the galaxy, where we have high-density gas and outflows. Whereas in NGC 253, it's more likely associated with cosmic ray dominated gas and not outflows, for example. So this is a huge difference already. So I could probably keep going with examples, but I think the main point is that once we move beyond the Milky Way, molecules can be dominated by very different processes. When we look at extragalactic molecular emission, we are typically seeing a mixture of many phases and densities within a single beam. So a molecule can trace one specific environment in the Milky Way, but may be dominated by a completely different process in an external galaxy. And as a result, the dominant excitation mechanism can shift compared to local conditions. So because of this, we cannot just go over and say we are mapping molecule and physical conditions like one-to-one, because it's rarely happening. And if we dig deeper, we can see that scaling of astrochemical diagnostics can be hard for different reasons also. So we have first obvious problem, which is the resolution, which I already mentioned actually, that we can beautifully resolve structures in the Milky Way, but they can be completely blended together in external galaxies. And second, we have observational limitations. And so currently one of the problems is like also we don't cover the full spectrum. We have a gap between JWST and ALMA, and many important tracers actually lie in far infrared. And so the frequency, and there's another point which was the frequency shift with redshift. So depending on what type of regime you want to look at, we will have also lines moving in and out our observable windows. And third, we have sparse constraints and ambiguity in physics in the extragalactic regime, which comes back to point one, actually, that with integrated emission that we are basically capturing, it's often very hard to be sure what combination of processes we are looking at. Because so in the Milky Way, the thing is that we can disentangle these individual processes and understand the chemistry in different settings. It makes it our perfect local laboratory, basically. So it's the place where we learn what molecular diagnostics actually mean. And so we know the physical environments, we have this multi-wavelength coverage, we have archival Herschel data in far-infrared, we have Spitzer, for depending on the species also of interest, but we had SWAS, we had Odin, and we can still obtain in the Milky Way this direct chemical constraints from detailed studies. So this is our ground that we actually have for testing the assumptions that we'd like to apply to external galaxies, like what are our diagnostics actually doing, what we think they're doing, or in other words, that this is where we can learn the language the molecules are speaking. So just to summarize, right, in the Milky Way, we can separate this physics cleanly, but it also that I mentioned the problems in the extragalactic, but it's still like with all of these extra detailed information, we still need the Milky Way, this details that we get from the Milky Way to understand what the molecules are actually doing and what they mean before we scale them up. But there is a limit to how far this local insight can take us. So, for example, of the star formation, right? So most of our detailed knowledge of star formation process comes within a few hundred parsecs of our solar neighborhood, and so the problem starts when we want to understand how galaxies build their stellar mass and how star formation looks like, where at the epoch where actually most of star formation happened, because this is not happening in the Milky Way. And this epoch is cosmic noon. It's between redshift 1 and 3, roughly. But it also means that we need to care about this galaxy scale star formation here. And so we need to look at this galaxy scale diagnostics. And we need to find a way to connect our local picture to this epoch that was way more active. And this brings a question. So can we take what we know from the Milky Way and stretch it all the way to cosmic noon? And one approach is to think in a bit of a way from like a bottom with this bottom-up approach or top-down approach. We have giant molecular clouds which host clusters, and these clusters are made up of individual protostars. So if we can understand how emission builds up from protostars, so now going back to the bottom-up approach, from protostars to clusters to whole giant molecular clouds, maybe we can then find a way to average that out over the galactic scales and say something meaningful about the feedback in the whole galaxies, and maybe then go and constrain something when we go to this regimes when we have to look at whole galaxies. So here, water would be a good candidate for this kind of scaling. So that's why I also brought up water earlier in the talk. So water is a very special species in many ways. It can be a bit problematic for some observers, but I think we cannot just deny that it's bright, it's abundant, and it's strongly linked to energetic processes like shocked, warm dust heating, and so on and so forth. And we found that there are correlations between water luminosity and source luminosity in galactic protostars, and we see similar trends between water luminosity and far infrared luminosity in external galaxies. But then, I mean, it seems like it could be a good tracer that could connect local star formation to galactic scale activity. But as we saw earlier, the interpretation can be environment dependent, so we have to be very careful. But it's still worth a try. And so another aspect is that water is observationally, what we have found was that protostellar water emission scales with envelope mass, which gives us this empirical foundation that we can use for building model that scales up to whole galaxies. And so in this way, right, if we know how much water emission we get per unit envelope mass, and we know how much clustered star formation we have, we can start to ask, what should a galaxy's water emission look like if it's just the sum of many protostars and clusters, right? Making the stretch from our galaxy, where we've noticed that most of star formation is indeed happening within clusters. So this is a motivation behind Galaxy in a Box, which was a model that I developed a few years ago. So in this model, we kind of tested this assumption whether we can scale up Milky Way and use as a template at a high redshift. So we used protostars as building blocks and connected them to molecular clouds and clusters and predicted the galaxy scale water emission from star formation. And it works quite well if you look at the lower end of luminosity range. But when we really compared our predictions with high redshift systems, dusty star forming galaxies with very high star formation rates, and even if we applied very high star formation rates, we still systematically underpredicted the water emission by at least 2 orders of magnitude, which told us that there must be additional physics or different excitation pathways that become important in the system. So whether that is far infrared pumping or something else, that's yet to be discovered. But we did this simple test to this, it's like physical, like this thought exercise, whether we can do that, and tested that out. And the answer was, unfortunately, we will be missing emission at high redshift. So if we cannot just simply jump directly from the Milky Way to high redshift, maybe you can use nearby galaxies like M51 and NGC 253 as intermediate laboratories. But even there, we have the same fundamental problem, right? We can resolve some structure, as you can see on the slide, but we are still mixing phases within one beam. And these systems sit between local clouds and high redshift galaxies, and they remind us that they're always dealing with this multi-phase, multi-process gas. And there will be a lot of processes also depending on where we look at these regions, what is really happening behind the beam. So this brings us to the central molecular zone, which is a very crucial piece of the puzzle. So since we can't just, for example, in the case of star formation, can just jump into very distant objects, assuming that what is tracing star formation here will be perhaps just also tracing indeed at similar levels star formation in external systems. And the intermediate galaxies are still providing some ambiguity. Maybe there is still something in the galaxy, and that is indeed potentially central molecular zone. So the central molecular zone is string-like accumulation of molecular gas in the innermost few hundred parsecs of the Milky Way. Already during the last PCAST talk, we had some information about the central molecular zone and its magnetic fields. So it was already quite clear it's a fascinating place. But let's just recap, right? So we will have in the CMZ, we have the central supermassive black hole, Sagittarius A star. We have the highest number of supernovae per unit volume, and it's extremely compact. It's 0.1% of the galaxy's surface area, but it holds up up to 10% of its molecular gas. And on top of that, the conditions in the CMZ are like warm gas, warm dust, high densities, elevated cosmic ray ionization rates, strong UV fields, X-rays, very high cosmic ray ionization rates compared to the galactic disk. There's a lot of turbulence, including widespread shocks, and essentially it makes excellent local analog of extreme star forming environments and the starburst nuclei. And so even though the current star formation rate in the CMZ is lower than we might expect from the dense gas component, for me, for example, right, chemically and physically, it will still remain a very instructive environment to understand. Because when we think about that, right, observations are one side of the story, and we still have to, there's so many questions, we have to compare a lot of regimes, dwell deeper, understand what we are looking at, but we can perhaps help ourselves, and that can happen with the chemical modeling. And we can use chemical models to understand these extreme conditions. And one of the codes is, for example, UCL Chem, which we develop here in Leiden. So it's a time-dependent gas grain chemical code, which is widely used in astrochemical community. It includes modules that will help us understand the warm-up around hot cores, shocks. We can change, modify irradiation, cosmic rays, and so on and so forth. But basically combining such chemical models with physical prescriptions can build chemical blueprints that can link chemistry to specific physical processes. And we have done it successfully over the years, not just with UCL Chem, all the codes, for example, of Garrett's Magical, to understand and dig deeper in galactic and extragalactic sources where we have this huge confusion limit also in the central molecular zone. And here's just one of the examples of a study of how H3O plus and SO was changed as a function of cosmic ray ionization rate in NGC 253. But let's come back to the CMZ. So in the recent project, we decided to go into the CMZ direction, and we built a large grid of models that is tailored to the CMZ-like conditions. So using UCL Chem, we explored here a wide range of cosmic ray ionization rates, UV radiation fields, enhanced temperatures of the medium, right? So we have this warmer dust as well. We have higher densities overall, and it's basically we try to build a representative environment of what we can infer from the CMZ. And so when we look at that, we also have the shocks. We have protostellar objects ranging with different final temperatures. But the bottom line, we look at very extreme conditions. And we made some of them a little bit broader so they can be used with, for example, extragalactic observations if someone wants to make this kind of comparison. And as a side note, all of these models are completely open to the public, so there's a link in the paper. But I think the point was that we decided, and we built a library of chemical behaviors under extreme conditions, CMZ representative, and compare those observations of the CMZ. In our case, it was for the ACES, which is the ALMA CMZ Exploration Survey, that looks at CMZ in unprecedented detail, sub-parsec resolution in band 3. And basically with this library, we will be able to understand a little bit more what we are looking at in the CMZ. But it's also a key step to do this kind of calibration if we want to connect CMZ to extragalactic regimes. So just a quick note for because it's astrochemistry in the end. We focused on representative set of molecules in band 3 that we were able to model and that were covered by the ACES observations. And some are typically known to be shock sensitive, some are more cosmic ray sensitive or tracing dense colder gas. Depending, I highlighted 3 species that I think I already mentioned before as the ambiguity when we look at, especially at extragalactic. But yeah, the goal was to understand how these species behave under CMC-like conditions, which ones are robust, which ones change a lot, and what combinations might act as good diagnostics in environments where our traditional tracers are less well understood, because also for some of these species, these are the conditions for which we didn't really cover them well observationally. And I don't want to go too much into details or methodology here, but I wanted to show an example of some hidden relationships we may still see with models that can help us understand a little bit better the behavior and correlation of some species, right? So here is, we are looking at how abundance of species change with in different temperature beams. We see maximum and mean abundances versus temperature. So for both shocks and this, we have mechanical processing, so in shocks, but also thermal processing in this gas around hot cores. And when we look at HCN and HNC, if we look at them separately, just as species that are just changing, their abundance may change with temperature, they show only weak dependence on the temperature. The maximum abundances are fairly flat across a broad range of temperatures. We looked at, it's like here, this is the overlapping range between shocks and star objects. But then if you look at them together, we will start to see that in this warmed up gas, so these protostellar objects, their abundances correlate in a way that does encode some temperature information. And in shocked gas, that correlation largely disappears. And for HCN and HNC, right, this is not a shocking information because they have been used throughout different works and different regimes as potential tracer of temperature. However, there's again this problem of interpretation and where we look at the two, because some studies will indicate that they are more affected by cosmic rays, and some will say that they are far UV radiation thermometer. So there's this kind of nuance that needs to be taken into account when looking at the ratios. But still, we looked at this extreme environment, and when we started to break it down, we are seeing that these underlying relations in the molecules that may be important when we are looking at this ratio at certain conditions that are similar to the CMZ. And cosmic rays are very important for the chemistry overall. And we also saw that in our models where we had this enhancement in cosmic ray ionization rate. And also cosmic rays will be one of those things when that becomes important when we start going through different regimes. And so in our grid, which was slightly extended central molecular zone range, we found that they, together with temperature, were among the key drivers of the chemistry. And there are some species, but there were some clear groupings of species. Some species were clearly normal. They have this very flat behavior or relatively flat behavior. So they're kind of normalizers if you want to build up molecular ratios. But some others respond strongly to the cosmic rays, and some will respond in a very coherent way. They will have this change that's consistent across the whole cosmic ray ionization range, for example, HCO plus H2CO, CH3SH. And some will be more affected by cosmic rays only in a certain type of regions. So, for example, around thermally processed gas and not mechanically processed gas. So this can be very useful for a separation of the underlying energetics, for example, right? Whether we are looking at gas that has been dominated by shocks, or whether we are looking at the gas that's more likely thermally reprocessed. So this is the kind of underlying information we can also take out. And then for a reference, we did compare our models to the CMZ observations, to observations of exactly 40 molecular clouds in the CMZ. Basically, this is just for shock models, because when we look at molecular clouds observations and we have the modeling, the shocks is what we are more after, because of this widespread presence of low velocity shocks propagating likely through the CMZ. And we are seeing that all of the observed clouds fall nicely within the predicted ranges of abundances. But the best matches usually correspond to this short evolutionary stage in the shock models, where we are within the shock, where the temperature is changing, the density is changing. And this is, again, this moment when we are getting this feedback from the physical side, from chemical models, when we want to do this reverse engineering and understand what we are looking at. And basically, it reinforces the picture that the CMZ is highly turbulent, and that what we are capturing is this recurrent or frequent shocks going through the molecular clouds of the CMZ. And now going to the far infrared a little bit. So I focused mainly on the chemistry and the problems, and the observational side. A lot of that was in the submillimeter. But I did mention water quite a lot. At the beginning, when we did this testing of whether we can use water emission as we use it in the Milky Way in extragalactic regime, where most of star formation happened. So the point is that if we are interested in star formation, we need the critical piece that is far infrared and infrared overall. So here we have a plot from Kasia et al. 2018, which shows star formation rate density. Basically, the point is that beyond redshift 2, our infrared coverage becomes incomplete. And beyond redshift 4, we are running into more problems. So basically, we are missing the dust-obscured star-forming population at high redshift, which limits our current understanding of star formation in the early universe severely when we are reaching this redshift level of redshift 4. And if we want to connect the star formation and astrochemical picture across cosmic time, we need something that will fill this gap. And we need to understand these dusty star-forming galaxies, like with the infrared probe, far-infrared probe. And so with Herschel, we've learned a lot about one of those tracers that can be used for star formation, but overall about the picture of star formation. But in case of water, right, one of the most informative water lines will lie in the infrared, which can be at the moment is in our galaxy is impossible really to see because we have the blockage by the atmosphere. And so for things like clustered star formation and the contribution from protostars across the full mass range, we need those far infrared lines. And we now need to understand the contribution of different excitation to the observed emission. But I think also we do need to understand how much, if we want to, for example, use this kind of calibrators or tracers like water, we need to understand how much water there is in our galaxy. And for that, we need a far infrared probe. Also, if we want to cover nearby universe, for example, to complete the information, because at the moment we are looking at a lot of high redshift systems with water, for example, because of the shift in the frequency that allows us to observe them. But we cannot cover the whole range because we are missing the probes for that. And we need sensitive far infrared instrument to go back and understand what is really happening and revisit things we have also established with Herschel. And yeah, I think that's the whole point, because we can do the connect the feedback with chemistry and extend Milky Way and CMZ diagnostics to galaxies across cosmic time. That will give us a picture that we are still missing. And just to summarize, I wanted to just point out that the chemistry carries the imprint of physical processes and gives us powerful diagnostics of star formation and feedback. And these diagnostics are environment dependent. And so we need the Milky Way, and especially places like the CMZ as a calibration laboratories. And chemical models can let us connect this resolved local physics to integrated galaxy emission and identify robust and sensitive tracers because there is too much that we are capturing, and we need to put everything, put the whole picture together. And when we want to have the full picture, however, and for example, look at many of the key lines like water, lines that are responsible for cooling, then we need the infrared, where we currently lack coverage. And basically future far infrared missions like PRIMA will give us the wavelength range that we need to connect these diagnostics across cosmic time. So thank you very much for your attention, and I'm happy to take any questions.
Thank you so much, Kasia. All right, we will take questions. Okay, I have one to start off. Part question, part comment, as it often is. So I was wondering, you talk about, definitely focusing on the central molecular zone of our galaxy as this highly resolved region. And one of the reasons to do this is the difficulty of dealing with mixing phases in a beam. And I was wondering, like, I know that's certainly a function of resolution, but is that also a function of the level of activity? So some of the things that I work on are fairly high resolution observations, like higher than alchemy of NGC 253, for example. And even then, once you get sort of these superstar clusters, you can end up having, whether it's a function of perspective or just very fast evolution, right? Things that are, the nascent molecular cloud, the cluster, and even supernova remnants all existing in a very compact area. So I wondered if you could comment a little bit more on like how does it become futile at some sort of high activity level to really be able to separate some of these phases?
Yeah, so I think there are many ways we can tackle that. I don't know if maybe I could have just rushed through everything, because I see I did take less time than I anticipated. So sorry if there were like lacks of logic in what I was saying. But for basically, of course, there's one part, right? We are averaging a lot of information in one beam. That's one part of the story. But there is the part of the dynamical history of the region, and the history of the feedback and what is really happening. So they are very different, but maybe at some level they can be a little bit similar. Because, for example, if we like in the CMZ, right, there will be feedback may be a little bit more, in some places, maybe more evolved, maybe fresher when we can capture that closer to cut it on ACT and see what kind of chemical information we are getting. But this is where exactly what we need when you have all of this hyperactivity happening, where we may use things like chemical models or even MHD simulations coupled with chemical models to understand how the chemistry changed with time after so many different events. Because also another thing is, right, when we look at some region where we are either losing resolution or there is a resolution that we are having, but there's too much happening, it's also fair to say that perhaps this emission will be dominated by one of the processes, and it's also fair if that's dominant process. But we may try to tackle that, what's happening, because there may be a way where, let's say, if you have multi-diagnostic of like different molecular lines that will have a very specific, very unique features, assuming certain mix of processes that can be assessed either by combination of observations with chemical models and MHD models, or models with, or just purely models, and see what we are getting, because there are many species we are using that we are observing, but there's still much to understand how the combined effect, how different species that, where we put them together, can tell the story of what happened. The resolution where we cannot see that, but another one is that we need to also capture the feedback a little bit better and understand that. So it's good to have as many observational constraints of the signatures of the feedback that we are looking at, wherever it means, and then also constrain potentially how these feedbacks look like in, for example, molecular emission, whether we can put them together like puzzles and get more information, and then use that to understand these hyperactive regions. Because I mean, obviously we'll have a lot of information that we have to tackle. We have the X-rays, we have not just PDRs, X-rays, cosmic rays. There will be shocks, and how does that stack together, and whether there is a much of a difference, because maybe there is not. Maybe there will be just one major component and the rest is just minor. So there's a lot of information that needs to be, I think we still need to revisit a lot of things we are looking at from many angles, and not just molecular, and then not just simplified, for example, chemical models, but also maybe processed MHD models, and see where we're getting, because maybe there's just it doesn't make any difference, or maybe there's a huge difference depending on how we look at that.
Awesome, thank you so much. Any other folks, feel free to raise a hand, just ask, or put something in the chat. Okay, well, thank you so much, Kasia, for your talk. As a reminder, these are all recorded and posted on our YouTube channel. So if you missed another talk, you can always go there to see what's been going on. Please go ahead and join us next month when we'll have Grant Donnelly talking about high Z pHs. And until then, take care.
Thank you. Bye.